So, uh, a very good afternoon to one and all. So, today we are going to discuss about the contents and some of the numericals and assignment problems related to the week 7. So, week 7th is already over, and we have covered up till week 6 in the live interactive sessions. The last week we have covered what's related to the molar properties, partial molar properties, mixture properties, and somewhat related to the Gibbs-Strom equation and some of the numericals and many more things related to the uh, Raoult's law, Henry's law, and the numericals related to that. So this week is from the week 7. So we'll start with that for the week 7 live interactive session today. So I welcome you all on the NPTEL online course certification on chemical engineering thermodynamics. So this course is offered by Professor Kargi Das. She is a professor in the Department of Chemical Engineering at IIT Kharagpur. And a little bit about myself. I am Rajpush Shivam Kumar, and PMR scholar in the Department of Chemical Engineering at IIT Madras. Okay, so we'll start quickly with week 7. So we are almost halfway completed for the Chemical Engineering Thermodynamics first part course for this semester, and we are almost in the week 7. So today also week 7 will be over, and we will be left with almost like 5 live interactive sessions. So what I will suggest is that please do look after all the live interactive sessions we have till now, including today live interactive session. Please do let me know if you have any questions, any issues, any confusions related to any of the concepts and the assignments or the tutorial problems we have discussed during this live interactive sessions. Apart from that, if you have any issues related to the assignment problems that has been on the SWAYAM portal, on the NPTEL SWAYAM portal online, and it's the answers has already been uploaded till week 7 or week 8. Please do let me know if you have any issues in that, so we'll be able to try to solve out before the final exams. Okay, even in the live interactive sessions, if you are able to ask me, that will be good because I can solve it at that time earlier. So week 7, and the week 7 content is somewhat like this. So it is going, what you're going to discuss in the week 7 is related to the mixtures, and like partial molar mixture property we have already seen in the last week 6. In this week they talked about the partial molar properties and the partial molar fugacity. Okay, so in the last week we have seen what is fugacity coefficient, activity coefficient, and somewhat related to the Raoult's law and the Henry's law concept and the assignments and tutorial problems related to that. So we quickly start with, we will first go through the content and we'll start solving some of the numericals. So first is partial molar property. So like this I have discussed in the last week also, but we will quickly rewind it. And okay, and similarly for pure species, the partial molar property is equal to the actual property. Now if you take in an open system, where the number of moles can be changed. Suppose if I take an open system where the number of moles can be changed, so I can write the change in the Gibbs free energy to the number of moles so like this. And then Okay, now if we try to simplify the above one, uh, suppose I will write now what is chemical potential. So these are just reminding for what the topics we have already covered. This is related to the chemical potential. Okay. And how chemical potential can be related to the Gibbs free energy for a species I. Therefore, if you see these equations, we can relate mu I equal to uh, del of Ng by del Ni into Gi. So this is one relation, and the other topic that is covered is that in a case of a binary mixture, since we are going to discuss about related to the mixture properties, suppose we have a binary mixture of the components are 2 for phase equilibrium. Or liquid and vapor phases. Therefore, mu1 of liquid is equal to mu1 of vapor, and mu2 of liquid is equal to mu2 of vapor. Now, another thing is that, so like I mentioned, the total property is a summation of I, xi, mi bar, right? And another one we have already covered in the last week is the Gibbs-Stone equation. So I'm just getting a recap of all the things we have covered in the week 6, and we are also seeing what is to cover in week 7. Therefore, now will be 0. Okay. Another thing, in a binary mixture, constant temperature and pressure. So this is one equation we have seen. So just like distributing this equation into 2, Okay. Now, if you say at a finite, at a pure component limit, if I say the component has a limit, suppose if it's a pure component, okay, the partial molar property is the same as the pure component property. So if I said if a pure component is having a limit, I can say that the partial molar property is similar to the component property. Okay, so this is one thing, and at infinite dilution, okay, so this is the last one. If I say at infinite dilution, what will be the mi bar is equal to mi infinity? That is, the partial molar property is same as the pure component property if I take as a at infinite dilution. Okay, so these things you have to remember because it can be asked in the terms of 1 mark MCQs in the final examination. And similarly, we know that enthalpy H is equal to internal energy plus the work done pressure. Its partial molar property can be written as partial property component I is equal to mu I plus PVI. So this is partial property. So this is what you've written in terms of the partial molar property. It's an analogous to its partial molar properties. Similarly, VdP minus SdT, right? So we are doing a partial differentiation, and we know that this is Tg equal to VdP minus SdT. For flow system, and this is for constant composition mixture. Okay, the content that has been covered during the week 6, and we have also seen what has been covered during the week 7. It's much more related to the partial molar properties mostly, and the binary mixture components property, and the partial molar viscosity and that all. Okay, so now what we'll do, we'll try to look out for the some of the MCQs first of all, then we'll try to go to the solving some numericals. Okay, so if you see combining rules for gaseous mixture predict, so look at the first question and we're going to look at the MCQs also. So what this is asking is that combining rules for gaseous mixtures predict mixture constants in terms of pure component constant, interacting parameters in terms of mixing parameter, both A and B or neither A and B. So if you see mixture rules, gaseous mixture rule predicts the interacting parameters in terms of the mixing parameters, not for the individual components, right? So the correct answer will be B. Why B? Because combining rules for the gaseous mixture predicts interacting parameters for in terms of the mixing for the components, not for the individual components, right? So the correct answer is B. Okay. Similarly, for the second one, if you see combining rules for gaseous mixture predict. Sorry, this one is a similar one. or it has been copied twice. No issues, just look at the first one. So it's the correct answer is B actually. Okay, we'll go to the second one. So partial molar property. Now what is partial molar? Like we have seen, it is an intensive, extensive, does not depend upon the composition of solution or not an additive. So the partial molar property, the correct answer will be is an extensive property. So like I mentioned, it depends upon the temperature. It doesn't depend upon the volume. It is a function of the temperature, pressure, and the number of mole of the components I. So like I mentioned up here, the partial molar property. Like if you see and go through, so this all partial molar property is a function of temperature, pressure, and number of moles. Okay. So I will write up here also. So if I write. Okay. So it's a function of temperature, pressure, and the number of components I, or the number of moles of the components I, and it's not dependent on the volume, so it is an extensive property. So extensive properties are the properties which are independent of the volume system. So the partial molar property is an extensive property. Okay. We'll go to the next one. So which of the following statement is false now? Oh, wait. Oh, sorry. This is partial molar. Sorry, guys. Just there is one mistake I made here, because I think of extensive, but actually I'll give you the correction. So because I remember something while discussing the initial content. So the partial molar property, they are independent actually. Independent of the total amount of each constituent. That's why it's an intensive property. Okay. Please make these corrections. Sorry for that. Because I was looking at some other point of angle, but actually, once I look at the formula, it's an intensive property, not an extensive property. Okay. I'll go to another one. Which among the following statements are false? This question talks about the partial molar properties. The first one says, for pure substances, the partial molar property. Just one. For, for pure substances, the partial molar property is equals to its molar property. Maxwell equations are not applicable to partial molar properties. Partial molar property can have both negative and positive values, and partial molar property represents the contribution of individual components to the total solution property. Now we have been given to say which of the statement is false. So if you see, the first one is the partial molar property represents the individual contribution of the components to a solution property. So this one is true. We need to ask to carry out the false question. So B1 is gone. So partial molar property can have both positive and negative values, like we have seen in the bit 6 content. We have solved some of the numericals. So this one is also gone. For pure substances, partial molar property is equal to molar property. That's we have seen during the initial content. We have seen like the partial molar property is equals to its molar property for the pure substances. So the only remaining question answer is the false statement is this one, that is Maxwell equations are not applicable to partial molar properties, because we have already seen Maxwell equations can be related to the partial molar properties, and I have also shown Maxwell equations here. Okay, so Maxwell equations can be related to the partial molar properties. So the only incorrect answer is B. Okay, now we'll go to solve some of the numericals. So the relative volatility of component 1 and component 2 in a binary mixture is equal to its vapor and can be expressed as. Okay. What is relative volatility first of all? So relative voltage can be given by a symbol of alpha, and it is one P1S by P2S. Now we know that saturation pressure is equal to, so this is from the Raoult's law, and we have solved these numericals, like 3-4 numericals in the last week also. So we say alpha equal to y1 by x1, x2 by y2 equal to, and we say that x1 plus x2 equal to 1, so this will be 1 minus, sorry, 1 minus x1 divided by x1, 1 minus y1. Okay, so this will be, and this can also be written as, so let's see what is the correct answer. Sorry, just write it again. Okay. So now if you see, the correct answer will be so it can be expressed as almost all of the above cases, like A, B, C. So I have, this is 1, this is 2, and this is 3. So the correct answer is all 3 of them. Okay. So is the relative representation of the saturation pressure of the vapor pressure of the composition 1 to the pressure of component 2. And then we can use the Raoult's law and can simplify this equation further. Okay. So like this I represented in the printed form, and we can use the Raoult's law here. So these two are the correct answers. So all three are correct. Okay. Next one. So what has been asked is that if the partial molar enthalpy of one component in an equivalent binary mixture, if the partial molar enthalpy of one component in an equivalent binary mixture is increased by a quantity dH1, then the partial molar enthalpy of the second component. So we've been asked to, for if an equivalent binary mixture is given to us, and they have said that the partial molar enthalpy of the component 1 is increased by this. 1 is 1, so the partial molar property of component 1 is given, and they are said if this, the second quantity is increased by dH1, then the partial molar enthalpy of the second component will be by what? 1. So we write, for, since it's a binary mixture, for an ideal so if I write, therefore well, here N1 and N2 are the number of moles of component. Okay. Therefore, if equivalent mixture is there, so therefore N1 equal to N2. This implies N1 equal to N2, then DH1 equal to DH1 bar equal to minus DH2 bar. So then the partial molar of second component will be decreased. So it's decreased by meters. So it will be decreased by the same quantity. So this is the correct answer. Negative DH1 bar is equal to minus DH2, so it's decreased by the same quantity by DH. Okay. So this is the simplest question. So this I have printed in reference. So for an ideal binary mixture, I have written this. and we have tried to solve it out where N1 and N2 are equal. So for an equivalent ionic mixture, what will happen is that N1 number of moles of the component 1 is equal to number of moles of component 2. This will try to sort it out, and this will be the correct answer. Therefore, H2 equal to minus H1 bar. So negative value means decreased. Correct answer is okay. Try to solve another question. We have been given 100 centimeter cube of 30 mole percent ethanol in water solution needs to be prepared. However, how many centimeter cube of pure ethanol? So we have given two components and it's a mixture of ethanol and water, and we have been asked to determine how many centimeter cube of, means how many volume percentage of pure ethanol and pure water should be mixed to obtain the same. The partial molar volumes of ethanol and water are given in a 30 molar percent solution are given to us. Okay, now we have to determine the volume fraction of both the things, like is it pure ethanol and water. So what we'll do, let's assign the components. So let's take ethanol as component 1 and water as component 2. Now we have been given as x1 is 30 more percent of ethanol, that is 0.3, and the remaining will be 1 minus 0.7. We have been given molar volumes V1 equal to 6.3 centimeter per mole, V2 is 17.8. Okay, now what we'll do is that since we know that the partial molar volume is written as bar. Okay, so the game is good. So x1 is 0.3, v1 bar is 0.7 into 0.8. So comes out to be 28.54 centimeters. Now, if you take the 100 moles, 100 centimeter of the solution, so the total number of moles turns out to be 100 divided by 28.54 is 3.5. Okay, similarly, now the number of moles of ethanol, 100, comes out to be 0.3 into 3.5, it is 1.05. Similarly, number of moles of H2 centimeter solution, it is 0.7 into 0.5 is 2.45. Okay, now volume. Now we have to determine the volume of ethanol and water to be taken. So volume of ethanol, volume of H2. So if you solve this, you have to take the number of moles multiplied by the molar volume. Comes out to 61.36. This comes out to how just by simply doing the partial molar properties simple calculation we can be able to define the volume fraction or the volume percentage of ethanol and the water. Okay, so the correct answer is, I think it's 44.32, so the correct answer is C. Okay, so this is one of the numerical that relates the partial molar properties of a binary component mixture. Now, what I was saying is that let's go to the other numericals and try to see out what other things can be done with these cases. So this was the first point in order to relate the partial molar properties to the component mixture. We'll move to the second question now. So this is the printed form of that one, and you have taken ethanol as 1 and water 2, so x1 plus x2 comes up to 1, x1 equal to 1 minus x2, and similarly x2 equal to 1 minus x1. x1 is given as 0.3 to us, similarly x2 equal to 0.7, and we have been given molar volumes of both the components. So we use the partial molar mixture properties in these cases for a binary composition and find out the total molar volume Vn. Now in giving the total solution volume, so the number of moles in that solution will be the molar divided by molar volume. So to find out the number of moles of ethanol and water in that composition, and the volume taken to be the number of moles into the molar volume. Okay, so this is how you identify the cases, because this thing have been given to us. We'll move to second question. Yeah. So chlorine gas obeys Van der Waals equation of state, which has a molar volume of 0.0224 meter cube per mole at temperature of 270 Kelvin. The Van der Waals constants are given to us as A and B. Okay. Determine the enthalpy departure function and entropy departure function of nitrogen at this state. So we have not discussed this enthalpy departure and entropy departure functions in the content, but we will try to cover it using the form of this, solving the numerical. Okay. So first we'll write what is given to us. So temperature is 273 Kelvin. Is 0.634. K is 0.054 times 2 minus 3 meter cube per mole. 0.634. Okay, and volume has been given to us as molar volume B is 0.0224 meter cube per mole. Okay, now what we do is using the Van der Waals equation of system, P is equal to RT upon mu minus B minus A by V. So this is what Van der Waals equation of state, and we have already seen during this week 4 and week 3 content. That is known as Van der Waals equation of state. Okay, so what we'll do, we'll try to put out all the values. Temperature is 273 upon volume is 0.0224 minus 0.054 times 2 minus 3 is 0.634 0.1. Comes out to be in the form of Pascal. Okay. Now we know that the enthalpy departure function is given by delta H star equal to minus RT minus enthalpy. Similarly, the entropy departure function is given to us by R ln P minus by RT. The only thing is that you need to put all the values in this equation. We have my pressure value, we have molar volume, R is 8.31451, temperature is 273, A and B values are given to us. Similarly, here all the values are given to us. All the values we get delta H star. So I'm just writing the final answer. You guys just put the values and you can find it out, because we already solved what is how to determine the pressure using the Van der Waals equation of state using this. So this is Van der Waals, that is equation of state. No, equation of state. So I'm writing the final answer. Okay, so let's try to solve it out. Add all the values into these equations and try to solve it out. So it's the simplest one. Just need to find out how to use this Van der Waals equation of state in order to determine the pressure value, and how to use the pressure values for the enthalpy and entropy departure functions to define what is enthalpy and entropy departure functions. Okay, so this is for the non-ideal systems we have done. Okay, now we'll go to so this is the form of a printed format that I have given to you guys. So if you see, like we have been given with the temperature, then given with the Van der Waals constants A and B, and we have been given the molar volume B. So these all things have been given to us. Now this is the Van der Waals equation of state. That is a non-ideal equation of state, and A and B are terms at the Van der Waals constants. So what we did is that we need to find out the value of P, because enthalpy departure function is like this and entropy departure function is this one, and both have the pressure terms in that. Now for the gas opening Van der Waals equation of state, the enthalpy and entropy departure functions can be written by this type. Okay, so we can just find out the value of the pressure P using putting all the values including the Van der Waals constants A and B into this equation, that is called Van der Waals equation of state. We have found out this value. Now directly insert these values into this equation. Then you can determine the entropy departure and enthalpy departure functions based on the Van der Waals equation of states. Okay, so it's the simplest one. So this type of questions can be asked in the final examinations, and it has been asked many times in the gate examinations also. Okay, we'll go for the last question for today. So what has been given to us is refrigerant of molecular weight 45 kilogram per mole exhibits a saturation pressure of 50.74 kilopascal and a latent heat of evaporation as 220.56 kilojoule per kg at 50 degree. Estimate the saturation vapor pressure of the refrigerant at minus 10 degree. Okay. So first of all, it's look at one point, it's confusing. We don't know what to find out. What we'll do first, we'll write out what has been given to us. So see what is given to us. T1 is 50 degrees Celsius. T2 is, we have to ask, they have asked us to determine as saturation vapor pressure of the refrigerant at minus 10 degrees Celsius. So we convert into Kelvin. Now the enthalpy of vaporization is given to us 20.56 kilojoule per kg, and the molecular weight is 45 per mole. Okay, Now what you can do is enthalpy of evaporation divided by molecular conversion. This turns out to be kilojoule per mole because kg gets cancelled out. Okay, that is what we have done is that the number of moles, in order to find out the number of moles, equal to given weight by molecular weight. Okay, so that's what we have done here. That is 20.56 divided by 45. Comes out to be 220.56 45 is supposed to be kilojoule per. Now we have been given P1 saturation as 50.74 sorry kilopascal. Okay, this is given. Now they have been asked to determine the saturation pressure of the refrigerant at -T, that is P2. Now from so this one is somewhat related to an equation which is known as the Clausius-Kelvin equation, and how to use this equation for this question is the point of view. Now from Clausius Kelvin equation, ln of okay. So what you have to do, we have all the values of the entire equation. We have R, we have T1, we have T2. We need to find out P2 set. We have P1 also. So let's push all these values, and if you do it, the final values will be P2 saturation is will be exponential of all the values will be coming up here after putting all the values. So what I am expecting is that P2 S will come out to be okay. Just put all this value in this equation. And just try to simplify this equation. You can determine the saturation pressure of the component 2 at -10 degrees Celsius. So T1 is given, that is 50 degree, T2 is -10 degree. We have converted into the Kelvin. Then we have enthalpy of evaporation will be given to us. R is a universal gas constant 8.3451 joule per mole Kelvin. Saturation pressure 2 is given as P1 is given to us as here 50.74 kilopascal. Only to determine the P2. Just try to simplify, the P2 answer will come out to be 28.83 kilopascal. So this is somewhat related to how you can identify the saturation of pressure if the two if the mixture, if the components temperature is given to us. So this is somewhat related to the Clausius-Kelvin equation, and we have mentioned that equation here for simplifying this and finding out the answer. Okay, so this is the printed form, and so this is in the printed form. Now so this is the printed form. The temperature was given 50, -10. We have converted into Kelvin because we thought of using the Clausius-Kelvin equation. So this is in the form of Kelvin. And enthalpy of evaporation is given to us. R we know, T1 is given, T2 is given. P1 saturation is given to us as 50.74. We need to find out P2, and R is 8.851 joule per mole Kelvin or kilojoule per mole Kelvin. Okay. So what we did here in the first one is that The enthalpy of evaporation is given in terms of the kilojoule per kg, but the equation that we are going to use here is in terms of mole. So we have converted that into terms of mole. You can see here. So we have converted this in a number of kilojoule per mole, and we have directly used this value here. Okay, so don't directly just blind use the value that has been given to you in the question. Please to look at all the units. The unit has to like match at some particular point, because if you use the value that kilojoule per kg given directly into this Gaussian equation, your pressure will not be in the terms of Pascal or kilopascal. It will have a kg term there. So in order to nullify that and in order to make it uniform to all the units used in this Gaussian equation, we have converted that into the number of moles, that is kilojoule per kilomole, and I have directly used this into the values. Okay, so the final answer is 28.83 kilopascal. That is the saturation vapor pressure of the component 2 at minus 10 degrees Celsius. That is 28.83 kilopascal. Okay, so this is what I have for the week 7 content. So it's much more like related to like partial molar properties and mixture properties, and how to use this Cauchy-Scheffer equation, like Epstein equation, molar properties, mixture molar properties, and how. So we have seen some of the numericals related to that. Plus we have seen some of the MCQs related to the same content we have covered during the week 7 and the week 6. So this is what I have for today. It's a quick one because today is the shortest, I think so, the shortest live interactive session I ever have in this tenure. So I'm continuously saying, if you have any issues, anything you are facing difficulties while solving some of the numericals or the assignment problems, please do let me know in this live interactive session. You can go through all the live interactive sessions. It's been uploaded into the NPTEL SWAYAM portal, and all these presentations will be uploaded in the form of PPTs. You can go and have a look at that also. Plus, if you have any issues, please do let me know in the SWAYAM portal or in the forums. Share your feedback in the feedback form about this live interactive session also. It will be helpful for me to just like, we have like left with like 5 interactive sessions left. So I will try to improve more and more as per the feedback received from all the students. Okay, so thank you all for joining this live interactive sessions. We'll meet you next week at the same time on Saturday from 3 o'clock. Thank you guys for joining us to the live interactive session. Okay, that's here. Goodbye.